All right, can you see it now?
Yes.
Okay, so I'll briefly talk a little bit about the background. So in 2017, I was very lucky to attend How Can Nielsen's course, OpenFOAM in Chalmers. And at that time, I did a homework about fluid-solid interactions. And later on, I met Luo Feng, and because he's also working with the marine field and doing some research with the fluid and solid interaction. So at that time, we remained a very close relationship, and we are contributing continuously to work with OpenFOAM. And thank you, Luo Feng, to invite me to this workshop, and I'm very happy to give this tutorial. So, and also in the previous tutorial, I observed that there is a very strong delay in China. I'm not sure if it's my network or it's because of the Chinese network. So anyway, as some guys have pointed out, that if I want to switch my screens, I will give some seconds so everyone can see that. And if you observe any delays, so Luo Feng, you can maybe tell me so I can slow my pace. So today my topic is about the post-processing and function objects in OpenFOAM. First, I will give an outline. I think for most OpenFOAM users, especially the beginners, they tend to use PanelFOAM, which is mainly based on panel view, and this is the graphical user interface. So the user can do the post-processing interactively. In this part, I will give some introduction about the basic steps, and then I will describe some commonly used tools and filters. And in the second part, because OpenFOAM has its highest performance in Linux, and Linux doesn't have a very good GUI. So OpenFOAM also provides a lot of provide this command line interface, and it contains a lot of post-processing utilities. So in this part, I will describe some of the utilities and also talk about the sampling data and also do the runtime data processing. And in the end, I will give a summary about all this information. So first, the panel view or PanelFOAM. In most of the tutorials, the user is told to use PanelFOAM to view the results. And when you use PanelFOAM, it actually creates something case.openFOAM, because the panel view needs some file to read, and this PanelFOAM is actually a ramper. It's like a scripting to call panel view appropriately. In panel view, it already contains a lot of built-in filters for the end user to choose. For example, the commonly used ones are cutting planes to see the contours, and iso surfaces or vectors to show the velocity, and the streamlines, and even make some data plotting. A very good start is to go into the panelview.org and then just get on this, check this panel view getting started guide. So next, some basic training. Here I provide a lot of some tips when I use panel view. It also for me to take a while to realize that sometimes we just need to use we can use panel view to just directly read files with extension .form instead of using PanelFOAM. So the reason is that when you use PanelFOAM, it will generate a temporary file named case name.form. But if we want to skip this one and just touch an empty file called new case form or whatever with your name, and then you can just directly use panel view to read this one. So a benefit with this method is that In this way, you can load the decomposed case with panel view plus the case name .form. Because if we use panel form, it can only read reconstructed results. And if you go to check the tutorial files in a lot of the outrun script, the last step will be reconstructing the decomposed case. But it also takes time and the computational effort to do the reconstructing. So instead, we can just use this way to load the decomposed case without the reconstructing. In the following tutorial, I will use the motorbike tutorial as the demonstration to show how do we do the post-processing. So first, I will show you. We have a job box, and I have uploaded the tutorial case to the job box. So I think after the workshop, you should have the access to download this one. And it is a tutorial case with results, so you can just directly use this one. Otherwise, you can go to the OpenFOAM terminal and copy this file. So this motorbike tutorial is in the tutorial files. If you go to tutorial, then it goes to the tutorial file and go to incompressible simple form. And here there's a motorbike. So you can copy this one to your user directory and do the run the simulation and check the results. So if I go back to the presentation, first we can touch an empty file called case.form and then use panel view to read this one. So this one is actually doing an aerodynamic analysis of a motor. So we have the air is blowing in from left to the right, and the surrounding walls are moving wall boundary conditions, and the bottom wall is a wall. In this one, the first filter I would like to show is the slice. So the slice is used to show a result on a cutting plane. The important control parameters include the plane origin and the normal vector. So in this case, you see this white outline is the calculation domain, and this slice is you specify the origin of the plane and then you specify the normal vector of the plane. So in this case, it's a normal plane at y0 because the normal vector is 0, 1, and 0. Let's see if okay. In this way, we can color it by pressure or velocity, whatever. Then the next filter is about a stream tracer. So in this one, we can get the streamlines. And here, there are some important control parameters like integration directions. The options here is forward, backward, or both. So here, what I'm showing is only tracing forwards, which means that it only traces in one direction. But if I change to both, then it will also show the left and right directions. And also this seeds, the seeds type, the normally used one is the high resolution light source. And to use this one, you need to specify 2 points to make a line. And this one, you see that you specify the position of the starting point and the end point. And also for the resolution, it's a little bit down of this line parameter, which means that if you specify the resolution to 10, then between these 2 points, it will divide it by 10. So there will be 10 points as the source, streamline source. Another useful filter is the probe location. This is very good to show how to quantitatively show the field results. So if you select any probe, and then you can extract the velocity, pressure, and other fields on this one. To use the probe location, the user needs to input the center of the sphere, and then the radius is 0, which means that it's only 1 point. Also, it's consistent with this one. Number of points is 0. So when you click apply, then a spreadsheet will pop up, and it shows the point ID and the point positions and the corresponding result fields like velocity, kinetic energy, turbulence fields, and pressure, etc. And sometimes you want to plot the probe over line, so you can analyze how the data variable is changing over time. So in this one, with the probe selected, you can use the filter called plot selection over line. So in this case, you are plotting the data over this point over time. And by default, it will take all the fields. In this case, it's the turbulence fields and the pressure and the velocity. If you want to do only show the velocity, then in this plot properties, you can deselect all the others and only remain the velocity. Next is about plot over line. So sometimes we want to analyze how the field is distributed along a certain direction. So in this case, we can use this filter plot over line. In this case, if we want to plot the field right behind the motor, so we can see how the velocity is distributed along this line and what the pressure look like. In this case, the user needs to specify the starting point of the line, the ending point of the line. And here the resolution is the same meaning as the streamline resolution. So if you put 100, then it will sample 100 points along this line. But if you specify 10, then it will only contain 10 points. So these are the commonly used filters to do the post-processing, and you can easily say or choose them with filter under the first top menu and then filter. Okay, maybe I think I can show it here. So in this case, I load this case and the decomposed case because it has about 350,000 cells. So I use 2 processors to run it. So now I will just go through what I described in the presentation. So first, I do a slice. And we have some shortcuts here. It's X normal, Y normal, and Z normal. So in this case, I just select Y normal. And I deselect this show plane checkbox. And in the results, I could select pressure, go to the final step, and then rescale the legend. So we have a high pressure in the front and the low pressure in the back. We can also see the velocity, so we can clearly see the wake after the motor. Then next is the streamline. So in this streamline, here we can select the integration direction, either forward, backward, or both. So here I select forward. And in the points, I just select, I can also do it interactively to drag it. I'll use this P to snap it to the nearest point. So so far, I just do it like this and see. Okay, that's strange. Okay, I think I need to type this, otherwise it's not. So it's -1, -0.05, and 0 almost. Zero point zero two one. Okay, I need to select the case form instead of the slice. Huh. Yes, now it works. But the resolution here is too high. We have 1000. So if I just change this one to 20, so we see the streamline like this. The probe location, I'm not going to demonstrate that one. Okay, so I go back. Another tool that I want to show is about the selection display inspector. I found this one is very useful because you don't need to, it's similar as the probe, but you don't need to use the filter. So it's a very interactive way. To toggle this selection display inspector, you just go to view and then select this selection display inspector. And in combination of using this parameter selection control panel, so you can select cells or select points on the slice or on the domain to show the results. And here you have these cell labels. So with cell or point selected, then you can show the results of this selection. So with one cell or point selected, you can use plot selection over time, and it will generate a similar plot time history plot, similar as using the probe location plus plot selection over time. Then I think this is a very good way, so I want to show this one. So to toggle the selection display inspector, we go to views and click on this checkbox. So here we have the selection display inspector panel on the right. And this one is the selection control toolbar. So here you see that if I just hover on this one, it shows select cells on. So I click this one or use the shortcut S to select any of the cells. If I show the edges, and then I want to see the pressure on this cell. So I can, with the cell label P, so it shows the pressure on this cell is minus 0.12. And if I want to select more cells, you need to turn on this AND selection. With this selected, then you can again select another cell to show the pressure on this one. I think this is very interactive and it's much better than the probe locations. Then you don't need to do the types probe coordinates for each probe. So personally, I think this is a very good way. And you can also see the velocity. The velocity is shown in components, it's not the magnitude. And also some other fields like the kinetic energy. So the next part, I'm going to talk about the command line interface. OpenFOAM has a lot of post-processing utilities. So first, I'm going to talk about the form log utility. The form log utility is used to do some data extraction on the log file. It's very important to check if a case has been run to convergence, and a good starting point is always to look at the log file to check the residuals. So in this case, if we take the motorbike as an example, we go into the directory and then use form log with the input argument as log.simpleForm. So it will generate a directory called logs, and it will generate a lot of files with, for example, this clock time 0. I can turn on this laser pointer. Clock time 0, and we have this K0, K final residual 0, K iteration 0. So what it means is that it extracts the log with the initial residual of, let's take pressure. Initial residual pressure is named P0, and the final residual pressure is called P final res underscore 0. And the number of iterations taken to run to the convergence tolerance of pressure is called P iters and underscore 0. So it helps you to extract this relevant data to X, Y, or like 2-column data. Then afterwards, you can use any plotting tools to plot it. So in this case, I use the GNU plot. So in the terminal, just type GNU plot, and then for the logs, it's a common practice to set the y-axis and the log scale. And then we can use plot with the code logs and plot the initial pressure is P underscore 0 and with lines with the title. Okay, so I'm going to demonstrate this one. So in this case, I have already run the case with this all-run script. So I already have this log.simpleForm. So now I do this form log.simpleForm. And you see from the terminal output that it extracts the data of all these fields and create XY files for each of them. So now I list the files, and you see that in this this log directory is created and contains all the generated files. So next, I use GNU plot to plot the residual. So in the terminal, I type GNU plot, and then I type, first I set the log scale to the y-axis, and then I plot the data file to be plotted is logs slash p0, and I want to plot it with lines and with a title called initial pressure residual plot as an example. So now you see that you see the residual of the initial pressure. You see the plot of the initial pressure residual. It has been converged from 0 in the beginning, from 1 in the beginning, and then to almost 0.002 after 200 iterations. And similarly, you can check the other files. For example, the kinetic energy. So it converges to a similar level as the pressure. Okay, so to quit this GNU plot, you just type Q to quit. Next is about the post-process utility. There are a lot of built-in post-process utilities, and you can list them by post-process -list. Here is a snapshot of the list. The available configured function objects are 67. For example, this Q, and you can do some field manipulation of AND, or you can get the cell max or minimum values. And the streamlines is also an inbuilt feature. Turn on the pointer. Streamline is also an inbuilt feature, and you can calculate the verticity of the verticity field. So those tools are located in form etc case-sticked post-processing. So if I list that one, it has different groups like fields, force, graphs, or min, max, and probes. And this is like a predefined configuration files. So in the following slides, we will show how to use them. And the source code of these function objects is in the form src and then function objects directory. It's almost, the groups are quite consistent. So, which means this, the fields in the source function objects directory defines how we use fields functions in form etc case-sticked post-processing. And for example, if we want to calculate the magnitude of velocity, which is quite commonly used post-processing, we can just type post-process under dash funct, then with the code and the mag parentheses u. Next is, since we already have a lot of predefined configuration files in this directory, so how to use it? Which means for the commonly used ones are probes, single graphs, streamlines, and visualization surfaces. If we take probe as the first step, then one can always use form info to get a description of the function. So in this case, if I use form info probes, so here it shows a description. Write out values of fields from cells nearest to specific locations. So it tells you what does this function do. And to get this function, we can use form get probe to make a copy to the case directory. So in this case, if I use form get probes, it will pop up. It finds two files, and this one, the first one is probes, and then the second one is the configuration files. OpenFOAM will automatically suggest you to use one. So I just type one, and then I copy this one to the case directory. So the next step is you copy the default or the predefined configuration files from the built-in or the etc post-processing folder. Then you need to add it to your according to your concerns. And after the modification, and you want to use this function, you actually command postprocess -funct probes. And you can also put more arguments like latest time, or only do this post process on time 1 or time 2, whatever. And this one, I take this as an example. So after I copy use form get probes to copy the probe into my case directory, it looks like this. So first, it has an include file, and this include file is the configuration file predefined in this directory. What the user really needs to change is these fields, like which fields that the user want to sample data on this probe, and the location of the probe. A noticing thing is that you can put multiple probes in this list. And if you want to check how the configuration look like, you can go to this directory, and it tells you about the type of this one, and then which library is linked to this function. And also the write controls is every time step in this function. So after you use post-process func probes, then it will generate the post-processing probes directory, and it contains the probe data in this file. Alternatively, there is another way to just put all this in the contradict functions block in the end. And we will talk about this later in the next slides. And the second utility I want to talk about is the single graph. Again, you can use form info single graph description, and then this one is similar as the plot over line we talk about in parallel. So it's sample data along a line, and you need to specify the starting point and the end point, and also specify which fields you want to sample. To get this one, you use form get again. So use form get single graph and modify it to your needs, and then execute it with post-process funct single graph. In this case, I put this, it's a line starting with 2.500 and then end with 2.508. So finally, it will give me this output with the data on this line, and I can also plot it with GNU plot or any other plot tools to get the distribution, data distribution along this line. So next is the streamline. In parallel, one can also do this interactively, but when you do simulations, maybe you want to check the intermediate results and you don't want to open parallel every time. So this is a very good way to check the results during the run. So to use this one is similar as before. You use form get streamlines to get a copy of streamline functions, and the configuration is in the streamlines.cfg file if you need, and if you know how to change, then you are free to change it. Otherwise, just keep the default ones and modify the user inputs like fields and the state method. This one, it provides a lot of different methods like line cell and others. But in this case, we use line uniform. So you put this line uniform after the state method entity. And the detailed definition is in this line uniform block. Is starting point, end point, and the resolution number of points. In this way, it will generate the streamline VTK files, and you can just load the VTK files into parallel, and you don't need to do the streamline filter anymore. The last one is about the surface. The surface, you can get a copy of the default configuration with form get surface, and also check the CFG files for configurations, for detailed configurations. But in the types, the surface consists of X normal, Y normal, but they all belong to the cutting plane type. So besides this cutting plane type, you can also use iso surface or even some get the surface of the CAD model. And if you execute this function with postprocess dash funct surfaces, a subdirectory called surfaces on the postprocessing directory will be generated, and also it contains the VTKs. So you can use parallel to realize the surfaces like this. In this case, we say that in the last time step, last iteration 500, we generate the X normal, Y normal, Z normal, and we sampled velocity on it. Okay, so I would maybe take one probe as one utility as an example to show it in the terminal. So I can take probes, I guess. Actually, I already have one in this one, so I just rename it to another one. So I use form get probes. So it pops up and asks me which enter file number to obtain description. So I suggest, and it's suggested I type 1. So it says copying from this etc keystick post-processing probes and probes to the system folder. So at least the system folder, we can see that we have a new file called probe. This one is what I had before, and I just rename it to probes_org, so it doesn't matter. And if we look at this probe, I can use it, git it. system probe. So the default probe location is 0, 0, 0, and the fields to be sampled is pressure and velocity. So in this case, if I change this to, I don't know, 504, and change another one, and another one, let's say, keep 0, 0, 0, and then save this one. So now I do this post-process function and probes. So you say that it creates, it executes this function for all time directories. In this case, I have only 0 and 200. And now if I go to post-processing, you see that we have this probes directory, and it has 0 file. So if I just say what values in there, probe 0, and take the pressure. So we say that on probe 0, 504, and we have 2 times, and we have 2 values for pressure, and the same for probe 1. But I think this one is maybe out of the domain, so that's why it's infinitely high. But basically, this is the idea of using the built-in utility to do post-processing with command line. So to summarize the utilities, so first of all, the general steps of summoning are use form get to make a copy of the desired function, and then you edit the files in the system directory, and then execute post-process function dash funct, and then plus the function name. Then you check the result in the post-processing directory. But some comments is that nearly every function has the CFG files included, and it indeed improves the readability of the code by only listing the most relevant entity to the user. But it also reduces the flexibility for some beginners. They don't know how to change, or they don't dare to change the CFG files. So it's a trade-off. And then the post-process utility is normally used when the simulation is finished. It's not a runtime or real-time post-processing procedure. So in the last comment is that this post-process utility works in the way of rereading the results folder. So depending on how often you save your results, your post-process utility will only get data of your saved results, which means in this case, if I only have 0 and 500 time directory, then when I use post-process utility, I can only get data or extract data from these 0 and 500 directories, because these are the results I saved in this case. But a lot of times we want to do the runtime data processing. We don't want to save the result let's say every 10 iterations, but we want to save it every 500 iterations, but get post-processing data every 20 iterations. So how do we do that one? Then in that case, we need this runtime data processing, which means that we don't need to wait until the simulation is finished to do the post-processing. The post-processing is done simultaneously with the simulation. So to perform a runtime data processing, the way is to include the function inside contradict. To include the functions, there is, if you check the OpenFOAM user guide, there is one option to use this hash include function syntax, the keyword, and then put the function name after that. For example, if I want to include the probe function into the contradict function blocks, I use this hash include func with probes. Just be careful that I don't think the user has access to change the name of this. So for example, if you use hash include function probes 0 and you have system probe 0, I'm not sure if it will match or not. But I think it's safe to just keep the default ones, like probes is just called probes. Don't try to modify it if you want to use this way. So after you include the functions in contradict, you can run the solver as 0. In this case, since I'm using 2 processors, so I use MPI run with 2 processors and then run it in parallel. So in this case, let's say the probes or the sites, it's written every 20 iterations, because in the contradict we set our write interval is 20, so the result will be saved every 20 iterations. And also in the function configuration files, for example, this graphs.cfg, the write control is set as write time, which means the function will be executed when the solver has a new write. So these two are consistent. Write control write time is equal to write control with write interval 20. If you want to have a more frequent sampling, so you can change this write control to time step and then put another entry like write interval 1. So in that case, it will be sampled every time step. For more information about how to use this write control and the time control, you can check this table. So you have different options specifying time step or write time or runtime or adjustable runtime. Another thing to notice is about if you include these function blocks in the contradict, and when you execute the solver in the log file before the time starts. So here is time 1. Before the time starts, you will see some output reading the functions you defined in contradict. So in this case, I have defined set line, and then I have defined streamline, and I also have defined some normal and iso surface in this surface function. The second option of doing the runtime data post-processing is to use, instead of using this hash include funcs keyword, one can also expand the included files and just directly code into the functions here. And the general syntax is you have these functions, and then these curly brackets is the most outer curly brackets, and inside this functions block, you specify a sub-function or a function object name. So here maybe it's function 1, and then the type is a probe, and then after this function 1 curly brackets, you can specify function 2, which can be a streamline with type streamline with different libs. So in this case, you have more control and you have this all functions in one block. So if you want to modify anything, you don't need to go into different subfiles in system folder. You can just directly change the control parameters inside this control dict and inside this functions block. And there is a detailed description in this in the source code, which is located in form src OpenFOAM database function objects .h. So let's go to this one to have a quick look. Copy. Oh. Yes. So here is the description. So OpenFOAM includes a collection of function objects selected by the user at runtime to manipulate simulations and provide mechanism to extract fields and derived quantities. So alternatively, the same action can be executed after simulation using the post-process command line option. And this is the syntax or the format of writing the functions inside control dict. So you have this function object name 1 and name 2, etc. And here in this one, this table explains some important entities, like the type is always required because you need to specify the type of the function object, and the lib is always required because depending on which function you need to link to different libraries. And some other optional entities is like write control to specify how often you want to write out the post-process function, and the write interval. And next one is the time control table, like I mentioned before. Okay. So in the original motorbike tutorial case, there are 3 runtime functions in control dict, and it is written with the hash include keyword. Please note the difference between this hash include func and hash include. So this hash include func is like a keyword to tell OpenFOAM that you need to read this function in the system directory. But if you use this hash include one and with this quotation, so it will just it's like you compress you define every code in streamlines in a file named streamlines and just put it here. So this line 49 to include this one actually will go into the streamline file and execute the code line by line inside it. So to conclude, so hash include is just a shortcut to go into this file and read the lines line by line. But include funct is more like another function to call this probes function. So they are not the same. Yes. So here, if you would like to use this more complex way to write in functions, you can of course choose this one, but it's identical to just put all the functions and expand all the code and put it inside here. For example, the streamline is identical to put the function object name streamline and then put the code here. And the cutting plane, you put another function cutting plane and put the code here. So it's exactly the same. To summary of this runtime data post-processing, we have you see that we can write out the data more frequently. With the post-process funct, it can only extract data depending on your saved results. But with the runtime post-processing, you can extract data depending on your write control and the write interval setup. So a few comments is that the user is always recommended to modify the write control entity to have more frequent sampling. The default one is write control is the same as the write interval, but you can always change this to write control method time step and then write interval, let's say every 5 time step or every 10 time step. And then the sample data, for example, like this, is data with 3 columns containing the time and the pressure or velocity, depending on what you selected. So you can plot this by any plotting tools. Okay. Time is running out, so to summarize that, we have talked about how to use Parallel or Paraform to do the interactive post-processing. And next, we also talk about some utilities, for example, form log utility and post-process utility to do post-processing in the command line interface framework. And in the end, we also talk about how to do the runtime post-processing instead of doing the post-process utility after the simulation. Yes, that's all my tutorial. And if you want to practice, you are welcome to download my tutorial file with the link. And I have already prepared an all-run script. So let's see. So there is a test run called direct function.sh, which means that I directly code in these functions. And then there is another one called test run include functions.sh. So I use the include funct method. And also I have another script called test run to use the post-process utility. Okay, so but last, I just want to quickly show if you succeed, then in any of them, so you have the VTK files, so you don't need to do the this streamline filter, but you can use the post-process function to have this almost the same results as parallel shows. Okay, so yeah, that's all my presentation. Thank you very much.